Well, thank you. Welcome, everybody. I'm Walter Klein, and yes, it is my birthday, and I'm one of the mission directors here, and I get a chance to fly on a number of these aircraft, to include this King Air that you're looking at right now, as well as some of the other aircraft that you may have seen, the DC-8 and the Gulfstream. Those are all part of this it's mission director aircraft that are that do the airborne science stuff. So whether we're flying over Antarctica, looking at climate change issues, or in the case with this aircraft, the King Air, we're looking at surface water ocean topography. We pretty much cover it all. So the beauty of this airplane is that it's obviously smaller and has the ability to be operated at smaller airfields, whether it's in this country or hopefully internationally eventually. And this particular instrument that we're putting on right now is the first time it's ever flown. It's eventually going to go to space, and Dr. Moller will explain it in some more detail in a second. So, and then we'll leave that sound on. That sounds good. It means that your government is actually working around here. So we're integrating this particular instrument called AirSWOT, which will be flown over a long period of time, looking at littoral waters and other ocean areas. But eventually it'll be on a spacecraft. Once it's on a spacecraft, this is something that NASA does quite often, is that we'll underfly the satellite or the space vehicle to validate and to calibrate that particular spacecraft. This particular spacecraft has not even been created yet, or it's in the middle of it.
It's in development.
It's in development right now. So we'll talk a little bit more about that in some detail, but I'll turn it over to Dr. Moller right now so she can give you some idea about the AirSWOT instrument and give you how important it is.
So there's a mission that is a NASA satellite mission called SWAT, which is Surface Water and Ocean Topography. And this mission that's in development, I think we're pre-phase A, will measure currents, ocean currents from space, and also for the first time surface water. So basically do a surface water inventory. So where are our fresh water supplies, what's happening with the global water cycle, monitor lakes and reservoirs, and also river discharge on a global basis. This is really what we're measuring is basically heights and slopes of the water, which then we can infer currents. We can look at the surface water storage as it changes, and also the same thing for the coasts and the oceans is look at the currents and the transport of the currents in the oceans. This mission that's in development, we need an airborne sensor to firstly do some of the calibration and validation, and also do some of the development that we want to do pre-mission so that we're ready to go when the mission launches. And so that's what we're going to fly on this B200. So what we've done is we've developed this sensor that can kind of make all the measurements that the satellite measurement will make, but we have the advantage of being able to take off and then come back, look at the data, spend some time and study it, so we can truly be ready for when the mission comes. Then, when the mission comes, we've got something to calibrate that sensor that's up there, and we know what we're doing with the data. So, basically what we're going to do is we're going to look down, and we're using kind of a stereo vision type of approach, like we did with SRTM to map the world, give a topographic map of the world. We're doing that, but at a much finer resolution. So we're looking for centimetre scale height changes, so we can tell where the water's flowing from here down to here at a very fine scale. So it really is pushing. And the thing that's amazing is like with the shuttle mission that flew in 2000, where we did the topographic map of the globe, that had a 60-metre boom. SWAT will do that from space with an approximately 10-metre baseline, and we're doing that from this aircraft with the baseline about that big, so that you can see how the technology is coming to such a way that we can make centimetre level types of measurements with a system that's this big or that big from space.
Yeah. And just to elaborate more about the instrument, I mean, there's a lot of complexities in trying to figure out how to do something like this, and what I've seen just the past 10 years is the shrinking of these instruments. I would say 10 or 15 years ago, this instrument probably would have been triple the size, and
we wouldn't have been able to make that measurement.
Yeah, wouldn't be able to make the measurement either. So with the advent of the computing technology and to be able to record the data tapes, for instance, on the SRTM And it used to be an AirSWOT, which was the synthetic aperture radar that flew on the DC-8 that you may have already seen on the other hangar. The tapes were about this big. They were enormous, and you needed an army of guys to move them in and out, and it was a really big deal. The data storage on this is small little drives, not almost a thumb drive, isn't it? It's small enough to be able to put in your pocket.
Yeah, they're solid state drives, and you get terabytes per flight, as opposed to many terabytes.
Many terabytes just on an instrument. I mean, the instrument is about this high, okay, and it's really small, and that's very important because you can put it on a smaller aircraft like this. It's cheaper to fly because it uses less fuel. You can put it on many different types of instruments. So hopefully in the future there'll be 3 or 4 of these airborne instruments, and we'll be able to put one on an airplane on the east coast of the United States, and maybe in Europe we'll have one as well. As a matter of fact, this is a consortia of NASA and CNES, which is the French space agency, right? Yeah. So don't ask me how to pronounce the acronym, but CNES is.
It's in French.
It's in French. Don't speak French. So we're working with them, and hopefully this is usually what happens with instruments like this. Once you have a successful space launch, scientists are able to get the data, crunch the data, and there's always, you can never have enough data, especially something of this fidelity. So I envision more of these types of aircraft, or certainly the sensor, on other King Airs around the United States and hopefully in Europe as well. So you'll be hearing about this in the news within the probably next few years, hopefully sooner, as the data starts to get processed from space, or even beforehand from this aircraft itself. So this is where it really starts, literally at ground level before it goes into space.
So is this an RF sensor?
Yes, it is. It's Ka.
Synthetic app. Oh,
the wavelength is about 8 millimeters, and that's one of the things that allows us to get so much finer accuracy as we're moving to these higher.
So it's an array type, or
there is an array, but it's basically an interferometer. So you're looking at 2 angles and use the stereo to get the height measurement.
So what it looks like on the plate, you can't see it. It's actually sitting there in its nobleness off the aircraft right now, covered in special tape.
It's basically a cube.
Right, it's a cube, and on the faceplate, which sticks out from the aircraft about 6 inches with a fairing around it, if you look at it, there's other smaller plates or arrays. The radar are some around this big, this wide, and they're sitting out maybe a ½ an inch from the main plate, looking down at various angles, and you can see the angles of incidence from the aircraft over here. And when you look at it, it looks like a lot of little faceplates. They're pretty basic looking.
what sort of power output is it?
It's 40 watts.
And all that power is generated from the aircraft itself. Our aircraft are able to fly other types of instruments. Certainly, AirSWOT is primary right now, but within a half a year, there may be another instrument team from another center that wants to fly on board. So we can download the instrument and then put other instruments on board, and we provide power and inertial measurements, guidance systems from the aircraft that interface with the instrument. So that's what we're really good at here at Dryden's, to be able to do that. Short of plug and play, once an instrument has flown a few months with a couple of campaigns, we typically could take it and upload it and offload it within a week or 2. And then the beauty of it is to take it and fly it on other missions away from home base, whether it's here in the United States or around the world. So AirSWOT is the main focus right now for experiments right now.
So, elaborating on what Walt said earlier, so this SWAT has been funded as a NASA development, but it very much will support an international collaboration, and the SWAT mission itself is a collaboration with the French Space Agency and also the Canadians. So
you don't want to forget our cousins.
We don't forget our cousins, yeah. And so they will be heavily involved in working with us on campaigns, both here and in Europe, and hopefully in Canada. So it kind of enables that collaboration to continue.
So, you guys have any specific other questions about aircraft operation or about how we integrate things? I don't know what your time schedule is. I know you're. Yeah, go ahead.
So the tools and instruments that are used and put in and interchanged on the aircraft, when you collaborate with international organizations or third parties or corporations, what are the restrictions on the types of instruments that can be used and the type of information that data that can be collected, or is it free to?
Well, the data, that's an interesting question. We are looking at collecting science. Okay, so you have things that are, eventually going to be distributed worldwide. Obviously, sometimes things are proprietary if it's based on, they're developing a new kind of a science or a new kind of process. For instance, a university may have invested a lot in that. But there's always agreements laid out before we even disseminate any of the information, that, how that's going to be disseminated. We at Dryden are just the facilitator for getting the data. And oftentimes there are not holes, well maybe there are holes for distributing data, maybe a year or two, depending upon how the collaboration of scientists and engineers have worked. So I'm giving you a vague answer because it changes with every experiment. But we're not looking at, not spying on anything.
Yeah, well, that's what I mean is like national security wise, it's how much regulation is enforced.
Yeah, ITAR is a real.
ITAR, we are governed by ITAR, but once the data has got to a point that it's been processed sufficiently, so it's a science product as opposed to an engineering or technology product. So there is proprietary information in the processing techniques and approaches itself. But once you get to the point that you've got a height map of water, that will get shared and researchers can just request that data and freely get it once we get to the point of actually generating those.
It can be a complicated process because depending upon the consortia of people, but suffice to say when we'll go internationally, for instance, with other aircraft, we'll always have a media day, and people are welcome to look at the aircraft, and we bring people on board to let them know that we're not here, there's no nefarious activities going on, and we're really actually really very good at that. When you see the white airplane with the NASA meatball on it, we're here to help. It's not like we're working on things that shouldn't be spoken about. So I can say that from my experience with the airborne science side, which makes it very approachable for school children and for college students and everyone alike. So we're very open in that. But if you got people who are spending a lot of their lifelong, creating their PhDs and their doctorates over something, there's you have to be understanding of that, and that's very different for each instrument as we put it on the aircraft. The aircrafts themselves, nice Gucci paint jobs and all their beautiful airplanes, but this is a regular line aircraft. This is a King Air that is flown. You've seen King Airs all around the world. It's a very common aircraft. We create an environment within the aircraft so it interfaces with different types of experiments. That's what makes them uniquely different. Plus, we got the nice paint job and the best pilots.
What's an average mission profile look like?
For the structure of it, well, it's dependent upon the instrument. In this case, this instrument is wants to go as high as it can go for as long as you can go. So, which is this aircraft will go within the area here up to 35,000 feet for 4.5 hours and fly lines.
So you just like head out the Pacific and stuff like that?
Yeah, we're getting more.
So for us, we want to fly as high as possible, and the reason is the higher we go, the more SWAT we get for the range of angles that we're looking at. So the higher the better, and it's kind of a graceful degradation. But that's kind of, this aircraft is very appealing in that for the class of aircraft, it can go quite high. And then you're going into the next class, which is, a Gulfstream or some kind of jet aircraft. But there's advantages for being small and portable as well. So, and this one has some nice ports for our installation. So it's a good compromise.
What happens when you get for the instruments where you have a combination, a consortium of instruments, typically on the larger aircraft, we can do that on this one as well, but we're limited by space available and electrical power. You'll have one science team that needs to go high and fast and another one that needs to go low and slow, and then another group that likes to spiral down and another one likes to go straight and level. It's our job to coordinate all that and try to meet all those needs through flight planning and through consensus amongst all the scientists. And oftentimes it changes in flight. It's very dynamic. They might find a phenomena that's very interesting, and they'll want to do in situ measurement in that environment and spiraling down. So we can change it real time. That's why we work with the FAA closely and other operating organizations so they know what we're doing. In this case, one instrument straight and level for as high as you can go. But it's never that easy with the development of an instrument. I would not be surprised if we're going to find some surprises, as you always do with an instrument. So typically we're going to fly, crunch data for a few days, fly, crunch data, and then we're going to, the adjustments, we'll have to remove the instrument, I'm sure, to tweak it and to do work on it. So that's what we do here.